Thank you both. Yeah, but today I want one more slide to these slides.
Okay, yeah.
Yeah, and afterwards, yeah, I hope that they will be updated on the website. Yeah. Today we are going to continue our discussion on non-commutative ordinary differential or difference equations. Yep, and last time we discussed some motivating examples. And non-commutative ordinary differential equations. And today we are going to discuss non-commutative ordinary difference equations, following the same structure as in previous time. And the last thing is related to methods that we can suggest in order to derive non-commutative ordinary differential equations or non-commutative ordinary difference equations, and we'll present some more examples about related to this part. Yeah. Well, let me move to non-abelian ordinary difference equations. Yeah, and let us start with setting and definitions. In fact, we want to work with the same algebra, but without derivation. Yeah? And instead of the derivation, we want to introduce a shift operator, similar to the commutative case. So we are working with unital associative algebra A, that is over the field C, which is given by direct sum this algebra is a group algebra, and in order to construct this, we consider groups J sub I with n big N generators, x1 sub I, x2 sub I, and etc. until n. And A is given by a direct sum of these groups. As I've already mentioned, instead of the derivation of A, we will consider translation operator or a shift operator. We will call a homomorphism T from A to A that satisfies the following properties. We have, let us recall that we have additional a central element Z, and T over Z is just Z, so it acts trivially on Z. We have parameters alpha sub I, and this action of T on these parameters is defined by a certain function f that we will specify a little bit later. And if we act on the generators x k sub A, we need to shift the second index of this generator. And this map we will call a shift operator on our algebra A. This is similar to commutative case. Now we wanna define a discrete system of non-abelian non-abelian discrete system. And again, we follow the same idea, the same definition as in the differential equations. So we call a set of relations of this form, where f, capital F sub k are some elements from our algebra A, And this set of relations is we will call a discrete non-abelian system, and this system can be classified into three types. And these types depend on the form of this function f. If if this function f is just a constant function, depending only our parameters a sub I, then we will call this system 33 autonomous system. So it means that in the case when t acts trivially on these parameters a sub I, we have autonomous system. If this function if this function is given by this formula, well, we shift sum of these parameters a sub I by 1. We will call this system 43 non-autonomous system and of additive type or D type. The last type is called multiplicative type or Q type. So when our function f is given by this relation, is defined by this relation, when we multiply sum of our parameters a sub I by Q or Q inverse, where Q might be as either non-commutative or commutative, but let us set that Q is commutative. Then this system 33 is non-autonomous and also and of multiplicative type or Q type. Well, in fact, in commutative case, we have a discrete systems of elliptic type, but since we don't know any examples of such systems in non-commutative case, we wanna skip this type in the definition. So this is the main definitions, and let us move to two examples. So one small remark about the rewriting of the system 43. We can introduce a notation in the following notation when we act m times by operator t on our generators xk. Probably I forgot to say that when I is equal to 0, then we have xk, just xk. We will omit the second index of our generator. And when we act m times by this operator t on the generator xk, we denote this action by x k sub m. So, and then by using this notation, we can rewrite our system 43 as a system of non-abelian ordinary difference equations. In particular, let us consider the case when n is equal to 1. And then let us present all these three types of non-abelian ordinary difference systems. The first one is just autonomous. We have a parameter alpha that doesn't depend on the index m. The second one is non-autonomous system of additive type, or of additive type, sorry, because our parameter alpha is shifted by m. And the last type is also non-autonomous, but of multiplicative type, because we have here this this multiplicative constant. yeah, this is just some kind of an illustration. Yeah, and next remark is the following. We can consider our discrete map, our discrete system as a map from our algebra A to our algebra A in the power of n, because we have n generators and yeah, n generators. Yeah. And it's convenient because we wanna introduce, we wanna study first integrals of our systems, and in particular, if we look at this equation from example 1, this map is just given by, this map is just given by this scaling, where we have denoted x1 just by x. Yeah. Now let us discuss first integrals. Yeah, we will call an element I, capital I, from our algebra a first integral of system 43 if in terms of phi, recall that phi is a map that we've just considered. If we act by this map phi on this element I and again obtain the same element I. For instance, let us consider case when n is equal to 4 and consider a map of this type. Here we have four initial functions y. I need to say that it's not necessary, but we can restrict ourselves for m greater or equal 0. And here we have four initial functions. For instance, when m is equal to 0, we have y1, y2, y3, and y4. So therefore, this equation can be rewritten as a map from A to A in the power of 4. And this map is in the coordinates, this map is given by this formula. And one can verify that under this map, the function I of this form is preserved. It means that this function is the first integral of this non-abelian discrete map. Why we're interested in this discrete map? Because it's related to the well-known or so-called Somos-4 equation. This Somos-4 equation, classical Somos-4 equation, is given by this formula 52. And again, if we rewrite this discrete equation as a discrete map, one can verify that this function I, capital I, is the first integral of this map. In fact, in fact, we can start from this equation 52, introduce some notation in order to introduce new variable y sub m. I'm not sure that I can write it right now, but yeah, it has the form of the ratio of 2x with different index m. And then by taking the then by taking the difference of these two Thomas 4 equations with different m and with different notation for the variable y, we can derive our equation 49. But in this sense, we will call equation 49 a non-abelian analog for the Thomas 4 equation, because starting from the commutative one, we can rewrite it in the form 49, but for commutative variables y. Now let us move to Lex pairs. And so for each three types, we want to define Lex pairs for these systems. Let us say that lambda and q are central elements of our algebra A. Let us start with the autonomous case. Let system 43 is autonomous. And suppose that it's equivalent to equation 53 with some matrices of non-fixed size, L, M, and M sub M. These matrices can depend on the spectral parameter lambda. And if this equation 53 is equivalent to our autonomous system 43, then we will call these two matrices, L and M, a discrete pair for our system, and equation 53 is then a discrete Lex equation for our system 43. Yeah. So this is just a discrete analog of the Lex equation in non-commutative case. Let now our system 43 is non-autonomous and of additive type, OD type. And let us consider two matrices, A and B, that depend on spectral parameter lambda. And now this dependence is crucial. Then if our system is equivalent to the equation 54, this is given by this formula, then we will call condition 54 is a monodromic discrete pair of additive type, and sorry, not our condition. These matrices are called isomandromic discrete pair of additive type, and condition 54 is isomonodromic D-representation of our system 43. Yeah. And similarly, we can introduce Lex pair for system of Q type. Yeah, let us suppose that our system is non-autonomous and of Q type or multiplicative type. And let us consider two matrices, A and B, that depend on the spectral parameter lambda. And here, lambda is also crucial, as in the previous case. Yeah. And if condition 55, which is given by this formula, yeah, let me mention that this argument is multiplied by Q. And then these two matrices, A and B, we will call an isomandromic Q pair, and condition 55, we will call an isomandromic Q representation of our non-autonomous system of Q type. Yeah. So, yeah. So in each case, we have discrete Lex pairs of autonomous type, of D type, and of Q type. Yeah. Let us look at the example. Yeah, we would like to present an example of the system of autonomous system. Yeah, in this case, the compatibility condition is of this form. Yeah, is given by equation 53. And let us return to our non-abelian Thomas 4 equation that we have already discussed a little. Yeah, so we set n to 4 and introduce, to make our formulas more compact, we introduce two functions, a sub m, that can be expressed in terms of y, and b sub m, it's also defined in terms of y. And consider two matrices, L(m) and M sub m. Yeah. These two matrices depend on the spectral parameter lambda. Yeah, we can see it here. Here, and here. Yeah, and if we substitute these matrices into discrete Lex equation 53, then we can immediately obtain that it's equivalent to our non-abelian analog for the Thomas 4 equation. It's given by formula 57. One more example is related to Thomas 5 equation, to be more precise, to non-abelian version of the Thomas 5 equation. Yeah, if we set n to 5, and consider these two functions a sub m and b sub m. And consider these two matrices, L, M, and M sub M. These two matrices are matrices of 3 by 3 sides. And they also depend on the spectral parameter lambda. Yeah. And again, if we substitute these two matrices, given by formula 58, into discrete Lax equation 53, we obtain a non-abelian version of the Thomas 5 equation. Yeah, that is given by formula 59. The form of these two non-abelian analogues are similar. The forms of these two non-abelian analogues are similar, but we have different indices. In these terms. And here also. Yeah. So let us, if there are no questions, I want to move to continuous limits. Yeah. Okay.
Okay, so I have one question. So
Okay.
how to find the first integral? So is there a systematic way to construct it?
Well, in classical case, in commutative case, we can, if we have a Lex pair of the autonomous system, we can consider a spectral curve, and then coefficients in front of the spectral parameters gives us first integrals of our system.
Mm-hmm.
Here we can do the same. We can do similar procedure, but the problem is how to define correctly the determinant of matrix or over algebra over non-commutative algebra.
Mm-hmm.
but if we use a proper definition, not the same as quasi-determinants yet. Then we can look at the coefficients in front of the spectral parameters, and these coefficients give us first integral of our system. But the point is that we need to define correctly the determinant of matrix over non-commutative algebra.
I see. So the previous example of the first integral is found by hand. So luckily you find it.
It was found, as I said,
Try and error.
This one, non-commutative.
For example,
We can. So this first integral was found as follows. We have for this non-abelian Somos 4 equation two matrices LM and MM. Then let us define the determinant of matrix A, that is just 2 by 2 matrix. I have not too much place. As follows: A11, A22 minus A12, A21. Then we can take the determinant that is defined by this formula of our matrix LM. It depends on the spectral parameter lambda, but in order to write the spectral curve, we need to subtract mu times the identity matrix, and consider this equation. This is the spectral curve. And if we compute the left-hand side of the spectral curve, we will obtain some polynomial in variables lambda and mu. And coefficients in front of these polynomials gives us this guy.
Okay, Okay,
but
thank you very much.
The crucial point is to define the determinant. In fact, this guy doesn't depend on the order of these multipliers in determinant. We can experiment and we can find out that we obtain the same expression.
Okay. Thank you very much.
You're welcome. So the last thing is continuous limits. As last thing in this part is continuous limits. And let me recall what is it. What is in the commutative case. Well, if we have some discrete equation, we can. It's natural to take its continuous limit. How to take it? Let us define new variable z. It is given by that is given by m multiplied by small parameter epsilon. And let us define a function x that depends on z by this formula. Then if we shift the index m, then we shift the argument of our function x as follows, as given here. And since this parameter epsilon is small, we can consider formal Taylor series near this point. And again, if we take a good change of variables, we can take the limit when epsilon tends to 0, and our discrete equation becomes a continuous equation. And let us look at example. consider the so-called QP1 equation. And let us take the following change. We introduce new variable y, dependent on the variable z. We set z as here. And in order to take a limit, we need to set this parameter alpha to be 4, parameter beta to be -3, and introduce this change for the parameter q. After substituting all this stuff into our equation QP1, we can take the limit when epsilon is, when epsilon tends to 0, and after the limit, we obtain the first Penlevé equation of this form. This is the reason why this discrete equation QP1 is called the discrete version of the first Penlevé equation. So, and it's and it's some kind of natural procedure that we wanna extend to non-commutative case. How to extend it? Let us do the same things, but but with but without some words. So similarly to the commutative case, we set the change of the size of our lattice and change of the main variable x sub m. And so now we can't talk in general, we can't talk about the Taylor series, but we still can use a change that is similar to the Taylor series. I mean that if we shift our index m by k, for each k we can define this polynomial in the parameter epsilon. And we can substitute all this stuff into our equation, difference non-abelian equation. And if this change of variables is good, we can take the limit. And then our discrete system becomes a continuous system. Let us look at the example. Let us consider non-abelian analog for the Köppen-Levy-1 equation. It's given by this by this formula. Here we have a non-autonomous constant alpha sub m, and that is just alpha multiplied by q in power m. Here alpha is non-commutative constant and q is commutative constant. And if we take the same change of variables but for this non-abelian equation, we can take the limit, and the resulting equation is given by this third order ordinary difference equation. In fact, it can be integrated. This stuff becomes just 6y in power 2. And after an integration, we obtain a non-abelian constant. So it means that after the limit we integrate our equation, and after the integration we obtain the first Penlevé equation that we discussed previous time. So the key point is to find a proper change or for continuous limit. But if we can find it, it gives us it can connect our non-commutative ordinary difference equations and non-commutative ordinary differential equations. So in this way, we can study the link between them. So, now I'm going to move to the last part, and any questions? If not, I want to proceed here. Let's proceed. So the last part is about methods that are useful for classifying non-abelian ordinary difference or differential equations. Well, in fact, we are interested in non-abelian analogues for the Penlevé equations. We know that we have some good example. For instance, some good examples. For instance, the matrix Penlevé-1 equation, that's of this form. We can recall it. And the main problem is how to detect non-abelian integrable analogues for the Penlevé equations. And in order to solve this problem, we follow the following classification steps. The first one is related to a criterion that allows us to select a finite list of non-abelian analogues. A little bit later, we will understand why we're looking for a finite list. Such that under commutative reduction, our non-abelian analog coincides with a given Penlevé equation. For instance, if we look at this Penlevé-1 equation and send the size of the matrices to 1, then our constant A can be absorbed by a shift of the variable z, and we arrive at the well-known first Penlevé equation. And in order to justify the integrability of our non-abelian analogues, we need to present their zero curvature representation or their Lex pairs. And and finally, we give the following definition: a matrix or non-abelian generalization of the Penlevé equation is integrable if it satisfies a criterion given in the item 1 and admits zero curvature condition, zero curvature representation. So let us look at methods that people have used in their papers. The first method is about matrix Penlevé-Kovalevskaya test. So we can study solutions of matrix ordinary differential equations, and by this so-called Penlevé-Kovalevskaya test, we can derive matrix analogues for the Penlevé equations. In particular, matrix Penlevé-2 equation is given by this relation. It's also a second order, but here we have a scalar matrix. Another method is related to a quantization of Poisson brackets for the Penlevé equations. And as a result, we can obtain, we know about quantum Penlevé-2 equation, quantum Penlevé-4, and quantum Penlevé-5. And for instance, quantum Penlevé-4 equation is given by this huge relation. But what we can see here, yeah, we see that this equation is the second order, and it contains, in addition to these two parameters, alpha 0 and alpha 1, one more parameter, h bar. Yeah, and this parameter is due to that we have a quantum Poisson bracket in this case. Another method is to study a connection between the non-commutative Toda systems and non-commutative Pinlevé equations. And by using this method, we can derive non-commutative Pinlevé 2 equation. And that's given by this relation. It's different from the matrix Pinlevé 2, because here we have a variable z that belongs to our algebra, or it's better to say to the ring, because because the solutions of this non-commutative Pinlevé 2 equation can be expressed in terms of quasi-determinant, and when we are working with quasi-determinants, we need to work with a ring or a skew field. Okay, and parameter alpha is still commutative. Yeah, and one more method, more natural than the previous two, I would say, is related to matrix Schlesinger deformations. Yeah, and by using this, by using this method, we can obtain matrix Pinlevé 6 equation, and since it's a master equation, we can in the sense that we can obtain from this equation the lower Pinlevé equations by using the degeneration procedure. Yeah, we can. So even in this case, we can start from matrix Pinlevé 6 equation, do some limiting procedures, and obtain matrix analogs for other Pinlevé equations. In fact, matrix Pinlevé 2 and matrix Pinlevé 1 coincide with matrix Pinlevé 2 and matrix Pinlevé 1 obtained in the paper by Bellandin and Sokolov. Sorry, but without this arbitrary matrix A. Well, there are more other examples of the Pinlevé equations, but today I wanna discuss only two from this list. One of them is related to non-abelian Pinlevé systems with Akamoto integral, and another one is related to reductions of non-abelian Hirota equation. Let us move to the first point. So what we want to do? What do we want to do? We wanna suggest a criterion, that is useful to classifying Pinlevé equations. And this criteria is the first integral of the corresponding autonomous system. So before, let us look at the example. In this example, we know that Pinlevé 2 equation has a Hamiltonian. It's given by this formula with a standard Poisson bracket for the variables u and v. And the system of motion equations is given by this second order system. Here, kappa is an arbitrary parameter. So this system is non-autonomous because it depends explicitly on the variable z. But we can, and since the system is non-autonomous, the Hamiltonian is not a first integral. But if we turn this system to the autonomous case, just by replacing this z by a new variable, a new parameter t, then this Hamiltonian h, will be a first integral of the system. Yeah. Now, now let us construct non-abelian analog for this autonomous system of the Penlevet-2 type, and for this Hamiltonian H, that in the autonomous case we will call the Akamoto integral. Yeah. In particular, we replace each commutative monomial by non-commutative ones. For instance, in order to rewrite this term to u and v, we write the following two terms: 2 vu plus beta multiplied by a commutator of u and v. Yeah, and beta is a scalar parameter that we wanna determine. And a similar way we rewrite this this Hamiltonian in the non-abelian form. Yeah, so it means that we need to rewrite the first term. Yeah, it has three non-equivalent forms in non-abelian case. Yeah, and in addition, we have two scalar parameters a sub 1 and a sub 2. And under the commutative reduction, yeah, this term coincides with the previous one, and similar for the system. So now we suppose we require that this integral, this non-abelian integral, is the first integral of our non-abelian autonomous system of the Penlevet-2 type. Yeah, so we require this condition, and this condition leads to a system, to a linear system for these unknown coefficients a1, a2, and beta. In fact, the system has a solution, and in this case, we have two solutions. The first one when beta is equal to 0, and the second one when beta is equal to -2. And these two solutions are related to each other by a transposition. Because in the first case we have just VU, and in the second case we have two UV. And these two terms are related to each other by a transposition. Well, in fact, we obtain an autonomous system, and in order to rewrite it in the non-autonomous form, we just replace T by Z, and obtain a non-autonomous system of the Penlevet-2 type. And in fact, this system is different from the system is different from this Penlevet-2 equation in the matrix form. So it means that one Penlevet equation can have different analogs in the non-abelian case. Okay. And we can do the same procedure for all Penlever equations, and we can classify them by using this criterion. And in fact, the results in equations are integrable because we can present their Lex pairs, the Mandromic Lex pairs. Yeah, let me move to the last part, to the second point of our methods. Let me open the whole slide. So in the commutative case, we know the following scheme. We can start from discrete Tode equation, or also known as the discrete Hirota equation or discrete KP equation, by a plane wave reduction, considered in the paper by Horn and co-authors. We can reduce it to the so-called Thomas N equation, or it's better to say a two-term version of the Gay-Robinson equation. And it turns out that Thomas N equations are in some specific cases are related to discrete Penlever equations. And it was also studied by Juan and his co-author Inoue. So we want to extend this scheme to the non-commutative case in order to obtain non-abelian discrete Penlever equations and non-abelian Thomas-N equations. In fact, we can introduce non-abelian analog for the two-dimensional discrete Tode lattice, and this non-abelian analog is given by this expression. Here we have a non-abelian variable theta that depends on three indexes. It's some kind of partial difference equation. On free this function depends on this element depends on three indexes L, M, and N. It has many nice properties, like it has Lex pair. Oh, pardon. Yeah, we don't look at the Lex pair here. It has Lex pair of different types. I mean, that scalar Lex pair, matrix Lex pair. It can be solved in terms of quasi-determinants. And we can consider continuous limits for this relation, and as a result, we can obtain well-known non-abelian discrete or continuous, semi-discrete or continuous Tode systems, Tode lattices. Now we would like to study. Now we would like to study plane wave reductions of this equation. Since our aim is to obtain discrete Penlever equations, they are non-autonomous. We need to introduce a non-autonomous constant to the Tode lattice, and it can be done by appropriate scaling. So, and as a result, we obtain this. We obtain a non-autonomous constant alpha that depends on indices L, M, and N. Well, so its form is given by this expression. Here, parameter alpha, constant alpha is non-abelian, and other parameters are commutative ones. Okay. not a good idea to not present plane wave reduction, but okay. So the plane wave reduction is just a linear change of our indexes while we just define a new function y sub m that depends on yeah, sorry. So we just send our element theta lmn to new function to new element y sub m, where m is given by can be expressed in terms of the previous elements of the lattice, yeah? L times L, L1 times L, L2 times M plus L3 times L3 times N. Yeah? And for specific values of these three constants L1, L2, L3, we can define this. We can define. Sorry, we can define this non-abelian. Sorry, I'm a little bit in a hurry. We can define this ordinary difference equation that we will call a non-abelian version of the Thomason sequence. And this Thomason equation is non-autonomous because we still have this parameter, this non-autonomous constant alpha. But now it has a little bit another form. Yeah. Okay. So again, idea is pretty simple. We start from our second order, our two-dimensional discrete ODE lattice. Since we want to obtain non-autonomous ordinary difference equation, we need to introduce a non-autonomous constant to this ODE lattice. So we obtain this formula 65. Then we take a plane wave reduction in order to reduce it to the ordinary difference equation. And as a result, we obtain formula 66, that is a non-abelian version of the Thomason equation. Now, how to rewrite this this ordinary difference equation in the Penlever form? We need to set one parameter of this equation to 1, and the second one then will be equal to 2. And we consider two different cases when capital N is greater or equal to 4 and when it's even, and when it's odd and greater or equal to 5. If we introduce these two changes of variable, so we introduce new variable u sub m that can be expressed in terms of y's. Then this ordinary difference equation can be rewritten in some form, and the first one leads to a non-abelian version of the QP1 hierarchy, and the second change leads to a non-abelian version of the QP2n hierarchy. But let us look at the Penlever one, and after that I will stop. So let us do this procedure for the first member of the Penlever one hierarchy. Recall that when we fix parameters as n equal to 4, r equal to 1, and s equals to 2, we obtain the non-abelian Thomas 4 equation. Yeah. Then by using a change of variables, we can, in order to use a change of variables, let us first rewrite it in the form 69. Then it's easy to see that we can introduce new variable u sub m, and then this equation becomes this equation takes the following form, and that we call Köppen-Levy-1 equation in the non-abelian case. And in particular, the second member of this hierarchy is given by this identity. Yeah, but in fact, we don't know. We don't know Lexper for these equations. But we're working on it. Unfortunately, we don't know the Lexpers for these hierarchies, even in the commutative case. So, and the last remark is about the connection between non-abelian Levy-1 equation and its commutative analog. So in fact, we can start from the commutative Levy equation, and we can rewrite it in the form of Köppen-Levy-1 given by this relation. How to rewrite it? Well, let us take two Köppen-Levy-1 commutative ones with different indices m. Note that they can be rewritten in the following form. We can divide the first equation by u sub m and u sub m minus 1, in order to obtain this form. And similarly for the second one. Then if we take the difference of these two equations, we obtain a commutative version of this non-commutative expression. Well, this is just about the connection that we can, unfortunately, we can't derive from this expression, the Köppen-Levy-1 equation of this form without knowledge of the Köppen-Levy-1, but starting from the Köppen-Levy-1, in the commutative case, we can rewrite them in this form in order to obtain commutative form of the non-commutative equation. So let me stop here, and thanks a lot for your attention.
Okay, thank you very much for very interesting talk.